In this video, we'll explore non-Euclidean geometry. Now, Euclidean geometry started with 5 postulates, but it was the 5th one that gave everyone so much problems, to the point where people were trying to prove the 5th based on the 4 first postulates, and it's been revised along the way to try to make it make more sense to people. The revision that we often teach our students is Playfair's revision, that through a given point not on a line can only be drawn one line parallel to a given line. But there have been other ways people have viewed it, for example the triangle alternative, Proclus' axiom, and it's because people continue to try to rethink the 5th postulate that we see the creation of both spherical and hyperbolic geometry. Now, spherical geometry started with the concepts from the Greeks. Ptolemy determined that the world was round around 100 AD, and they started to use that concept in the idea of how they calculated their distances and angles when dealing with situations on Earth. Menelaus then came up with the idea of the great circle being what would be considered a line on a sphere. And then from there, a lot of the major significant work then came from the Arab nation mathematicians. For example, Al-Jayana considered to write the first treatise on spherical geometry in its modern form, and then it's been continued to be improved upon from the Arabian mathematicians. And around 1850, Riemann formalized the concept of spherical geometry as well as elliptical geometry. Now, here are some of the basic components to understand about spherical geometry. The way that the 5th postulate is revised is that given a line L and a point P not on L, there is no line containing P that is parallel to L. And this is the fact that in spherical geometry, we consider only great circles to be lines. So, because lines have to split the sphere in half. And the only way that's possible is if two of the great circles intersect. So there's no way to make a parallel line in spherical geometry. Triangles are actually going to measure from 180 degrees to 540 degrees. And because there's no parallel lines, there can be no parallelograms. And there are no similar triangles. If you have a triangle, it is congruent, but not similar. Now, hyperbolic geometry didn't start to be discovered until the 1700s, when Saccheri worked with the idea of trying to prove the parallel postulate. He created the Saccheri quadrilateral, in which where you look at points A and D, or angles A and D, and call them summit angles. And we recognize that they have to have one of 3 options. They're either right, obtuse, or acute. If it's right, we have a rectangle. But then he started to look at, well, what happens if these angles are obtuse or acute? And what he noticed was that if they are both obtuse, that the sum is greater than 180 degrees, which contradicts the parallel postulate. But then he tried to continue to work on this quadrilateral with the acute situation, and because he got lost doing that, he never completed his work and then ends up losing all the credit he could have been known for non-Euclidean geometry. From there, the parallel postulate moved to, instead of looking at whether 1, 0, or more than parallel lines can be drawn through a given point. Gauss did a lot of work with this, and he thought that there was some other form of geometry, but just never published anything, so he didn't get credit for it. And the 2 men that end up getting credit are Bolia and Lobachevsky. And Gauss even wrote to Bolia's father commending his son for the work that he'd done, saying that he found the concepts that just had continued to elude him. And Bolia then accused Gauss of trying to plagiarize and steal his works. And the reason we give both of these men credit is because they published in the same year in different languages. Thus, it would have been highly unlikely one could have seen the other's work. Bolia published his in 1832 in the appendix of his father's book, and Lobachevsky was published actually in the Kazan Bulletin in 1829 and 1830, and was later published in German and French, in the hopes that he could draw a larger crowd to this concept of hyperbolic geometry. Now, when we talk about hyperbolic geometry, it's occurring in what we call a saddle, but often we use what's called Poincare's disk, which is looking at just one specific component to hyperbolic geometry, but allows us to view the concepts of hyperbolic geometry. And so here's a picture of what the saddle would look like, and this picture is one that we would say comes from M.C. Escher, and is one that he used to actually do quite a few of his hyperbolic geometry constructions and paintings. Now, what the fifth postulate states in hyperbolic geometry is that given a line and a point not on the line, there's at least two lines containing P that are parallel to L. Now, the key components are that parallel lines are not equidistant everywhere, so that's very different than Euclidean geometry. Also, triangles sum from 0 degrees to 80 degrees non-inclusive. We can definitely have parallelograms in rhombi, but it's not possible to make a rectangle. And there are no similar triangles, again, only congruent triangles.